In the next 3 slides, I'm going to talk about image logs like you have here. These are image logs and the tools we use to generate these image logs, which are the imaging tools. And you will see they are mainly in two forms. You can have others, but we're going to talk about two main ones. The first is this right here, which is acoustic borehole imaging tool. And Schlumberger's version is called UBI, some ultrasonic borehole imaging tool. So ultrasonic borehole imaging. And what it creates is this kind of images. And when this image looks sinusoidal, I mean this dark crack looking sinusoidal, it's actually an image of a planar fracture that cuts through the wellbore. What are these? These are the directions, right? You already know your directions. This is north, south, west, and east, right? So it's your wellbore opened up. So if you cut it this way, so you cut it this way and you open it, actually you just need to cut it at one point. If you cut it at just one point, say here, and open it up, right? So you're looking at the full circumference. And now you cut it at the north. So this is your north, and this other point is still north, and you have all the other stuff in between, right? And actually we go this way, which is clockwise. So next will be what? East, then south, then west, and that's it right there. So this is the circumference of the wellbore. And now I move on to discuss the tool that was used to generate this, which, like I said, is the acoustic borehole imaging. And you all already know this involves sound. So the tool has a motor like shown here, which makes it rotate. And by the way, it's the rotation that makes the planar fracture appear as a sinusoidal line. And what it does is it sends sound to the wellbore, so from the tool to the sides of the well, and measures the time it takes for the sound wave to return to the detector. And it's able to invert that and come up with this image. And that's what I try to explain here. It sends high frequency sound pulses to the sides of the wellbore, measures the time to pick up the sound wave, and that will indicate the circumference of the wellbore and rugosity. And what's rugosity? It basically refers to the roughness of the wellbore. So more precisely, it relates to the changing diameter of the wellbore as you go deeper into the subsurface. So the variation in the wellbore diameter with depth is precisely what rugosity is. And this tool is sensitive to that using sound. There is another tool which is actually more, I won't say necessarily more accurate, but gives you higher resolution, which is the Schlumberger FMI tool, Formation Micro Imager. Formation Micro Imaging tool. And unlike the previous one, which was UBI based on ultrasonic waves, this one uses an electrode. So you have 4 electrodes in this setup, and it acts like a caliper, right? So it feels the boundary of the wellbore, and it's able to come up with an image of whatever it sees on the wellbore. So if it sees fractures, it's able to come up with a high resolution on that. And this is just details about that tool. Important thing is this is based on electric signals, whereas UBI was based on ultrasonic signals, and the electric signals are emitted from those electrodes which sit on the caliper arms. So next I will show the images from both tools. So this is your Formation Micro Imaging tool. This is the ultrasonic borehole imaging tool. and that's the corresponding image you get. So this is the higher resolution. Although this has a lower resolution, you will wonder why use this, why not always use FMI? Well, it turns out FMI doesn't work well when you have oil-based mods. So we use the UBI tool in those cases. And you can also try to come up with an image of the wellbore using resistivity at the bits while drilling, but the resolution is very low, as you can see right here. So most of the time, if you're going to have water-based mods, you're going to see FMI is being used. And in the Volve project, I also shared these image logs for a couple of the wells, so you can actually see what they look like for a real well. Now we move on to StereoNet, and it's basically a way to represent the orientation of faults and fractures in 3D space. Of course, you can have different orientations. It could be vertical, it could be off vertical, it could also tilt, it could have azimuth, right? And not just deep. You can have deep, you could have azimuth changing. And there is a way to represent all of those for several faults on one plot, and that plot is your StereoNet. It looks like a scatter diagram designed specifically for faults and fractures. And the way it works is, imagine a hemisphere, which is half of a sphere, like you cut an orange in two equal halves, and you're looking down on the bottom half. That's your lower hemisphere. And this gray right here represents the actual fracture or fault. So it's inclined at a dip of about 45 degrees. So the angle between this fault and the horizontal is about 40 degrees. That's your dip. Then what is strike? Strike is the trace of the fault, plane on the horizontal. So this is precisely the strike. So that's the line the fault plane will make with the horizontal. So that's the strike, and this is the strike angle, right? It's north east 30 degrees. And now, how do you represent this fault that has a dip 40 degrees and a strike of northeast 30 degrees with the StereoNet? That's what you show here. So with the StereoNet, you're not going to draw the hemisphere, you're just going to draw a circle. And that circle represents this circle you see when you're looking down on the hemisphere from above. When you're looking down precisely on the lower hemisphere from above. So that's what you see here. So this fault plane will show up like this. Just imagine you're looking down on the orange that has a cut in it this way. It's going to look like this, right? And we actually don't use this gray because we can actually work with the pole. So what is the pole of that fault? It's basically where the unit normal to this fault. So I'm back up to the upper image here. Let me reduce the image. Okay, so this is the middle of the fault plane, right? Its normal will point downwards. And that normal, if you continue to extend it, will end up touching the surface of this hemisphere at some point down here. And if you look at where that point is relative to this view, it will be here. And that is what the pole is. So it's where the normal to that fault intersects the circumference of the hemisphere. So it's easy to see, right? Because this is about 30 degrees, you already know it's going to plot on the other side of this quadrant, right? Which is precisely here. If the fault were completely vertical, instead of dipping at 40 degrees, where do you think the pole will be on? So if it were completely vertical, meaning like this, then the unit normal will point this way, right? And it's going to touch the pole. If it were completely vertical and not south, then it's going to touch the pole right here, right? The default will like this. But because it's inclined, then it's going to move inwards and be here, right? I mean, not inwards, in the direction from west to north. It's going to move in this direction and will be here. So you would have had it here if it were completely vertical but with a strike of 30 northeast. Then because it's not vertical, it dips, then this actually moves in the interior of the circle, which is why it's right here, right? If it's completely horizontal, meaning parallel to this surface, then the unit normal will point downwards and will touch it. It will touch the hemisphere right down here, which will correspond to where? Right here, right? To be at the center. So that's how you interpret the stereonet. And I'll move on to the next slide in the next video.